Hey, 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 it's Mr. Pout! Alright, section 7-8 is called Geometric Sequences. And you may recall from a few chapters back we learned about arithmetic sequences. They are actually very similar, slight difference. So our goal for today, our learning target, is to write and use formulas for geometric sequences. Alright, quick vocab. What a geometric sequence is. Alright? A geometric sequence is one where to get from one term to another, you multiply by the same number each time. This number is called the common ratio, or usually our R. Alright? So, in our example, from each number to the next, it's multiplying by 5 every time. When we did arithmetic sequences, it was adding a same number each time. This is a different, it's multiplying. That's because we're in the exponential chapter, so it has to do with multiplication. And to find that common difference is you just take like 250 and divide it by 50 and you get 5. So you take one number and divide it by the previous term. Alright, identifying geometric sequences. Determine if they're geometric or arithmetic. So I'm going to actually ignore this right here because we just talked about this stuff, what it is. So ignore this for right now. Don't get too caught up in that. But I do want you to determine whether a sequence is geometric by looking at the pattern. So if the terms are found by adding or subtracting a constant number to each term, it's arithmetic. So those are the ones we talked about a while back, adding or subtracting. These are geometric if it's found by multiplying, we just said. So if you multiply the same number to get to the next term, that's what geometric is. And then the common ratio, or R, is found by dividing any term by the preceding term, the one before it. So, examples. Which of the following are geometric sequence? And if the sequence is not geometric, is it arithmetic? Alright, so, alright, letter A. 3, 6, 12, 24, 48. So it's not adding by a common number, so it's not arithmetic. But, let's see, multiplying. This would be times 2, times 2 again, times 2 again, times 2 again. So this is geometric because the common ratio, R, oops, would be 2. Alright, letter B, 3, 6, 9, 12, 15. Alright, that's not geometric because it's not multiplying by the same number every time. But it is adding 3 every time, which makes it arithmetic. Alright, number C, ooh, fractions. 1/3, 1/9, 1/27, 1/81st. I think, yes, this is going to be multiplying every time. It's multiplying by 1/3. 1/3 times 1/3 is 1/9. 1/9 times 1/3 is 1/27th. 1/27th times 1/3 is 1/81st. So this is multiplying by the same number every time, so it's geometric. And then letter D, 4, 7, 11, 16, 22. It's definitely not geometric. It's not multiplying by number. Let's see if this is plus 3, plus 4, plus... It's not adding by the same number either. So it is neither. Alright, so that's basically how you can identify if it's a geometric sequence or not. And typically if it's not geometric, then it is a arithmetic. But it might not be either. So, let's move on to finding recursive or explicit formulas. Now, we're going to focus more on the explicit formula for geometric sequences, but I want to show you the recursive formula as well. So any geometric sequence can be written with both an explicit and a recursive formula. The recursive formula is useful for finding the next term. The explicit formula is for finding the nth term, which would be any term, whatever number term you want. So you could find the next one, or you could find any one. This is the one that I like better. So, for geometric sequences, the recursive formula would be this. where a to the n, so that would be the nth term, is equal to a to whatever that term is minus 1 times the common ratio. Okay? You need to know that a to the first power is, a is just going to be a to the first power. Now, the explicit formula is a to the first power, not to the first power, sorry, a sub 1, um, which would be the first term, times the ratio raised to the n minus 1 power. Okay? So let's just do an example here. Write the recursive and explicit formulas for this. So it looks like it's multiplying by 3 every time. So that's the common ratio. So R is 3. The starting point, which would be a sub 1, is 7. So recursive formula would be um, a sub n would be equal to a sub n minus 1, which would be, yep, minus 1, times the ratio of 3. We don't know which one we're finding yet. The explicit formula, which I'm going to suggest using all the time, would be a sub n equals a sub 1, which is 7 for this one, times the ratio r raised to the n minus 1 power. So that's the only part you have to change the n. So, now you try. Find the recursive and explicit formulas for the following sequence, 2, 4, 8, 16. So I'm going to have you pause it right now and try to write both formulas, and then I'm going to show it to you when you play it again and compare. See if you got it, see if there's something you need to change, see what you got. All right, go ahead. All right, so I wanted to show you, I did make a mistake. I forgot to change in the explicit formula up here the r to actually 3 because the ratio was 3. Now, for this one, I want to tell you the recursive formula is so the nth term would be a sub n minus 1 times 2. So you have to have the one that's before. That's the problem here. You have to have the one before it. That's why it's a. So if you're trying to find the fifth term, you have to have the fourth term because that would be n minus 1 would be the fourth term and multiply it by 2. That's just basically what the geometric sequence is. Whereas the explicit formula, you can find any term no matter what you had, as long as you know the ratio. In this case, it's 2, and the starting point, which is also 2, and then you can plug in whatever term you're doing it for n. So that's the explicit formula. All right. Now, let's write a geometric sequence as a function. So these are, since they are like exponents, you can write them as functions. So a geometric sequence has an initial value 6 and a common ratio of 2, right? A function to represent the sequence, graph the function. So we're plugging in, we're gonna use the explicit formula, and we're gonna do 6 is our initial value times 2 to the x minus 1. So we're gonna use x instead of n now. That's all. The function looks like that. Represents a geometric sequence. Now, to be able to do that, we have to make a t-chart essentially to find the values. And this is all done here where x is 2, 3, 4, 5, and we have the ordered pairs. And once you plot those, then you'll see that since it's an explicit formula using exponents, it is going to look like an exponential function here when you plot those. So that's why this is part of this chapter, because geometric sequences are exponential, whereas the arithmetic ones were just were linear. All right. So if you were to do the same thing, and I tell you a geometric sequence has an initial value of 2 and a common ratio of 3, first write the function, and then show me what you would do to graph it. So let's actually do this one together. So I'm going to say if we're using the explicit formula, it would be a sub n would be this initial one, which is 2, times the common ratio of 3 raised to the n minus 1. So in function notation, that would be f of x, sorry, or y, but we'll say f of x equals 2 times 3 to the x minus 1. And then to find points to graph, we would make a little t-chart, x and y. So let's just say we have 1, 2, 3, 4, 5. Alright, filling in 1 for x, that would be 0 as an exponent then. And our that would turn 3 to the 0 power is just 1, so this would be 2. If we put in 2 there, we'd have 3 to the first power, so that'd be 6. And it's going to be multiplying by 3 every time. So I can skip plugging it in, and I can just look at this. Times 3 would be 18, times 3 would be 54, times 3 would be 162. So this is really going to grow fast when it's multiplying by 3 every time. And I'm not going to graph it right now, but it's going to definitely look like this. Alright, it's going to go straight up like an exponential growth function. Okay? Alright, that's geometric sequences as functions. The last thing I want to do is just a real world application of this. So let's read this together first. Two managers at a clothing store created sequences to show the original price and the markdown prices of an item. Write a recursive formula and an explicit formula. We're not going to do the recursive, just explicit for each sequence. What will the price of the item be after the 6th markdown? So, first sequence we have, here's our two sequences, 60, 51, 43.35, 36.85. Alright, now remember, to find that ratio, we have our starting point. Our first one would be let's see, is a 60. Now to find the ratio, you take any number, so we're going to do 51, and divide it by the one before that, so 60. And that'll tell us our common ratio. So 51 divided by 60 is 0.85. Now to double check that that's the same for everyone, we can take any number. So let's take 36.85 and divide it by the one before that, which would be 43.35. I think I just typed it in there slightly wrong. Actually, no, I think it's because these are rounded, but it is 0.85 again, so we're going to use that ratio. Alright, so the common ratio. Now, if you look at the one on the right, there isn't a common ratio because it's actually going to be arithmetic. It's going down by the same amount. So, both starting at 60. Don't like the recursive formula. But the explicit formula, we can't quite do it for the one on the right because it's not geometric. But it is, we can use the one that was arithmetic. So this is actually the arithmetic sequence. And over on the left, we plugged in 60 for the starting point, 0.85 for the rate, and raised it to n minus 1. And in this case, we're trying to find this after the 6th term, so it's going to be 6 minus 1. Well, I guess after the 6th term, so it'd be the 7th, so 7 minus 1. And we get a price of $22.63. Alright? So the price continuing the first sequence is $22 after the 6th markdown. The price continuing the second sequence is $12 after the 6th markdown. Because, alright, yeah. So that's how you use the explicit formula for real world problems. Now, I could have you do one on your own, but we just went through this one, and as long as you're able to do this, just take a look at it. You will have to do problems like this on your own. But it says write a recursive, and again, I need to just cancel it out because I don't like the recursive formula, and I think it's not as useful, not even close to being as useful as the explicit formula. But find the 8th term of the sequence. That's what you should be able to find. Okay? If you can do that, that's a good chance that you know what you're doing with geometric sequences. If not, um, take a look back at the previous slides and familiarize yourself with that explicit formula. But that's a good check for yourself for this learning target, which is to write and use formulas for geometric sequences. That's what section 7-8 is all about. I hope you got something out of it, and we'll see you next time.